Okay, so here we'll talk about two different functional groups, which is aldehydes and ketones. So aldehyde and functional group basically present here is a carbonyl group. It's called a carbonyl group. A carbonyl group basically consists of carbon and oxygen polar double bond. Okay, so in this case it's usually written as carbon double bond O, and then there could be some other group attached to it. Okay, this is called a carbonyl whenever there's carbon double bonded to an oxygen. In this case, this oxygen right here is more electronegative, so it has a partial negative charge. Carbon here has a partial positive charge, so therefore this bond is a polar bond. Always whenever you see a carbon double bonded to oxygen, it is a polar bond. Okay, which means this is creating a dipole, and direction of the dipole is going to be from positive to negative. Okay, now what are aldehyde and ketones? Whenever you have a carbon double bonded to oxygen with a hydrogen, that group is called a aldehyde group, and this is R. So basically you have any group of carbons. This is a chain of carbon, it could be anything. As long as it has one carbon which has double bonded oxygen with a hydrogen, this group is called aldehyde. It can also be written like this, or you could sometimes see it written like this, CHO group. That means this is aldehyde. And the ketone group here, ketone also is a carbonyl, so it has C double bond O. One side it has R group, the other side also it has a carbon or R group. So if this hydrogen is replaced with another group of carbons, that is called a ketone. So this functional group is called a ketone group. As long as you see C on both the sides, this could be anything, right? This carbon can have anything attached to it. As long as there is this carbon double bonded which is bonded to two other carbons, this would be ketone. As long as one of these carbons is replaced by a hydrogen, that would make it aldehyde. So those are aldehydes and ketones. Okay, so like it shows you here, an aldehyde is CHO, and a ketone would have two carbons attached to this carbonyl group. Okay, so how could you recognize it? Basically, whenever you see CHO, aldehyde. Whenever you see carbon with two other carbon, carbonyl with two other carbons, that's ketone. Okay, now let's see how would you name these. So whenever we are naming aldehyde, this is a little tricky one. For up until now, what we saw, the naming usually ended with the alphabets at the end. They were similar to the name of the functional group. For instance, alcohol ended with OL. Okay, thiol ended with thiol. But in this case, the name is a little different. Aldehyde, their name, you basically write the name of the alkane and replace the E of the alkane with Al at the end. So whenever you see Al, so basically it's going to be alkanal. You replace the E with Al. Whenever you see Al at the end, that is an example of an aldehyde. This is the IUPAC name. Sometimes very commonly used names for some aldehydes, which is called the common names, are formaldehyde, acetaldehyde, propion aldehyde, and butane. These are like some very common aldehydes. Their usual common names are ending with aldehyde. Okay, these names you are going to see very commonly in rest of this course, so I would advise that you memorize this as well. I will never ask you to name a compound like this, but sometimes in question I might give you something with a formaldehyde. So you should be able to recognize that form here means it's one carbon, and it's aldehyde, so that means it is one carbon with a aldehyde group. So if I were to, and two carbons would be acetaldehyde, three carbons would be propion aldehyde, four carbons would be butyraldehyde. Okay, so these are common names that will be used commonly all through this. Now if I were to ask you, can you draw the structure of formaldehyde? How would you draw this? Formaldehyde means there's one carbon, so I draw one carbon, and it's an aldehyde, which means it has to have this group. So now It's only one carbon, so which means I cannot add any other carbon. Now we basically just satisfied the octet of this carbon. So this carbon has how many hands already? 3. It needs how many more? How many total hands does carbon carry? 4. So it has already
3.
So it needs one more. So you draw one more hand and you fill it up with hydrogen.
Oh, we fill it up with aldehyde with the carbonyl group with the H.
With an H. So we already drew that.
And then wasn't it also like a carbon chain?
It's a carbon chain, but in this case the compound has only one carbon. So it would only consist of this carbon. There wouldn't be any chain attached to it, because if you attach a chain, the number of carbons would increase, right? So in this case, this is important. This is crucial, where students make a lot of mistakes. So I'm glad you asked this, because this carbon, the carbonyl carbon, is a part of that carbon chain when you count the carbon chain. So for instance, if we were to draw this acetaldehyde, acet means 2 carbons in total. So you draw 2 carbons first, and then you know it's an aldehyde. So aldehyde group would be double bond H. Now you fill it up, the rest with hydrogen. So this carbon has how many bonds already? 1, 2, 3, 4. It's satisfied. You can't add any more hydrogen. This carbon has 1. So how many more does it need? 3 more. So we add 3 more hydrogens. So important thing is, when you see an aldehyde or a ketone, in that case this carbon, which is regarded as a functional group, is part of the carbon chain.
So formaldehyde is the most simplest formula.
The simplest formula. 1 carbon aldehyde that is possible is formaldehyde. If we were to draw this 3 carbon aldehyde, how would you draw this? 1, 2, 3. 3 carbons. One of these carbon has to be an aldehyde group, which is double bond H. And if you recognize, this carbon will always be a terminal carbon. It has to be always a corner carbon. Why? Because whenever you draw this group, you see this group already has 1 bond with hydrogen and it has 2 bonds with oxygen. So it can only make 1 more bond. It cannot make any more than that. So it can only have a chain attached to it on one side. It can never have another chain attached here, because that's not possible. Right? So this carbon will always be a terminal carbon. Okay? And now let's complete this molecule. So this carbon has 1, 2, 3, 4 bonds. So this is satisfied. This carbon in the middle has 1, 2 bonds. So it needs 2 more. Perfect. This carbon has 1 bond, so it needs 3 more. So you put 3 hydrogens. So that would be structure of propion aldehyde. But that is common name. When I ask your name, questions would be majorly IUPAC name. So how would you name this? This is 1 carbon. So first thing you recognize, this has a functional group, which is an aldehyde. How do you name aldehyde? Aldehyde is alkane followed by Al. So if this was 1 carbon alkane, what is the name?
You put the formula there as well, or is it just aldehyde?
So this is 1 carbon. 1 carbon alkane is methane. Perfect. So now what? How do you name aldehyde? You replace this E with Al. So the name would be methanol. Okay. How about this? This, you see, first thing when you see the structure, you're like, okay, this is an aldehyde group. And how many carbons? Remember to count this carbon in. So this is carbon 1, carbon 2. 2 carbon means eth. Ideally, if there was no group, it would be ethane. But in this case, we replace E with Al. So ethanol.
Okay, that's not, methanol is an O, right? The alcohol, right?
Alcohol. Alcohol would be methanol. So alcohol gets all at the end. Aldehydes get al at the end. Okay. So in this case, this would be ethanol. This would be 1, 2, 3 carbons of propanol. Okay. And now you see that I'm numbering, starting my number from the aldehyde group. Why? Because aldehyde is given the preference here. So this is your functional group. So remember, your functional groups are given preferences. So in this case, this is a molecule of propanol, so this aldehyde group will always get the preference of being carbon number 1. So as long as this is present on carbon number 1, you don't have to write it, and aldehydes will always be carbon number 1, right? So you don't have to write exactly where the al is located. Okay, so for instance, you can see here, this is methanol, ethanol, propanol, 3 carbon with an aldehyde. 4 carbon with an aldehyde is butanol. And you should be able to recognize this line structure as well, because you would not always see it expanded like this. So when you're drawing the line structure of this, how would you draw this? Again, this is one corner, this carbon is one corner. So 1, 2, 3, 3 carbons, right? And now the functional group you will have to show me. So this would be double bonded to oxygen and 1 hydrogen. Okay, so whenever you see a group like this, that also means this is an aldehyde group. So whenever you write line structures, as long as there's a functional group, which is not just hydrogen, hydrogen isn't the functional group, right? Whenever you have a functional group, you have to show that functional group in the line structure. Okay. Perfect. So let's see, how would you name this? So this is an aldehyde. First, let's find our long chain. So what you're seeing here is, I have this carbon which will always be counted in my longest chain, right? So I could go 1, 2, 3. I could go down like this, 1, 2, 3. But that's not my longest chain. I can clearly see that's not my long chain. So I would go the other way. I would go 1, 2, 3, 4, 5, right? And I would always count it from right to left in this case, because my functional group is on the right side. So now if I were to number this, this would be 1, 2, 3, 4, 5. So my long chain here is 5 carbons. Whenever you see this double bond, just don't count this out. Don't think that, okay, this is not a part of the functional group. This is already part of our long chain. Okay, so what is the substituent here now? This is my substituent because this is outside my parent chain. So what is the substituent called? Methyl. It's 1 carbon. So this is methyl. Where is it located? Carbon number 2. So this is 2-methyl. And what is the name of my parent chain here? Pentanol. Perfect. So this is pentanol, and you put the substituents in front. So that would be 2-methyl pentanol without any space. So that would be the IUPAC name for this particular compound. And if you were to draw it from the name, you again start from the far right end, which tells you this is an al, which means this is an aldehyde. Then you see this is pentanol, which means this is 5 carbons. So I would draw 1, 2, 3, 4, 5 carbons. And 5th carbon or number 1 carbon. One of these carbons I know has to be aldehyde. I have to draw the al group first. So I would draw the al group right here. It has to be a corner carbon. Remember that. I could draw it here. I could draw it on the left side. It doesn't matter. As long as it's one of the corners, I'm good. And whichever corner I draw it, that has to be carbon number 1. So if I draw this 1, this is 2, this is 3, this is 4, this is 5. And then the question tells you it's 2-methyl, so it would be 2-methyl. Okay, so when you're drawing the structure, it really doesn't matter how you start numbering. You just have to remember, if there is a functional group, you number that first. Okay. All right, and then again is given in the slides. So if you ever forget it, you could read through this again. Okay, next we will talk about how do we name ketones. How do you name ketones? Their name, simply you write the name of the alkane again and replace the E with on. This is called ketone. So the name would be on at the end, means it's a ketone. Okay, for instance, if you see this structure right here, what do you see? I see that there is 3 carbons here and I see a C double bond O. This is a carbonyl group which does not have a hydrogen. So what does this look like? This looks like R, C double bond O, R, which means this is ketone. So when you recognize this, how do you count the carbons? You could go either way in this case, because this is also 1, 2, 3. If I start from this end, it would be 1, 2, 3, so it doesn't matter. So this would give me 1, 2, 3. 3 carbon means propane. Replace E with on, so it would be propanone. Okay. So I technically, if it was an alkane, it would be propane, but I replace the E with on, so it is propanone.
The name is ibuprofen name.
This is IUPAC name.
What about the one with the dimethyl 1 ketone?
Those you don't have to worry about it. So I'll talk about those as well, but if I ask you a question again, I'll be asking you IUPAC name. I'll never ask you common names, not in this case. Okay. So only time I'll ask you common name is ethers. Never any other compound, no common names. Okay. Next, in this case, why did I not put here that this is carbonyl group is located on carbon number 2? Should I tell where the carbonyl group is located? So you should tell where the carbonyl group is located. As long as it is not carbon number 2, you have to tell me where the carbonyl group is located. Because for ketone, if you understand ketone, the C double bond O will always be in the middle, somewhere in the middle, right? But as long as this is carbon number 2, I'm okay, because it can never be carbon number 1. It can only be carbon number 2 at least. So as long as it is 2, you don't have to tell me the number. I understand that this is carbon number 2. So if you give me propanone, the only way I can draw propanone is I would draw 3 carbons. And I know it's an on, which means I have to draw a carbonyl. I cannot draw a carbonyl here, because if I draw one here and I put one hydrogen, it becomes aldehyde. This is no longer a ketone. So only way I can get a ketone is if I draw this structure and then fill the hydrogens. So if, as long as it is carbon 2, you don't have to tell me. But if it is any other carbon other than 2, you have to give me the number of where the ketone is located. Okay. So for instance, if you're drawing butanone, if I give you the name, how would we draw this? Butanone. On means ketone. Ketone is C double bond O. I know that. Then I draw the structure which is bute. So bute is 4 carbon. 1, 2, 3, 4. Okay. Now this is 4 carbon. I know it's a ketone. I cannot draw ketone on the corner. Either I draw it on this side or I draw it here. There are only 2 options. And I can, let's say if I draw it here. And let's say I draw it here. Are they any different?
They're the same.
They're the same molecule. Only thing we did is we flipped the molecule. I rotated the molecule, because if I'm numbering this molecule, how would I number it? Again, I would start numbering from my right side, because this is the functional group. I need to give my functional group the smallest number. So this would be 2, 3, 4. So this is on second carbon. If I'm numbering this, I would start numbering from here. This is 1, 2, 3, 4. This is still on second carbon. So this is also 2 butanone. This is also 2 butanone. So essentially it's the same structure. So they are not isomers. They are the same structure. I just rotated it. So it really doesn't matter how you draw it. What matters is that you should know this is the number. The name didn't give you a number, which means it has to be the smallest number that is possible, which is 2 in case of ketones. Ketones can never have 1. Okay. So what would be the name for this compound? So first thing I recognize when I look at the compound is right here that this has a functional group. Right? What is my functional group? It's all single bonds, and then I see a double bond O, so I see a carbonyl, which means this is ketone. Now, how do you name ketones? I need to name the alkane followed by on. So let's find my longest chain. Longest chain is right here. I can start numbering from left to right or from right to left, it doesn't matter. It all comes out to be 3 at the end. So 1, 2, 3, 4, 5. So this is pentane on, I know that. And where is the carbonyl? Third carbon. This is not 2 pentanone, so I have to tell that the pentanone is on second carbon. Okay, so for instance, if I were to draw this 1, 2, 3, 4, 5, and I drew right here, so this would be 1, 2, 3, 4, 5. Now the structure would be called pentanone, but 2 pentanone. So 3 pentanone and 2 pentanone have the same molecular formula, but they have a different structural formula, which means these two are isomers. Okay, so make sure you understand that isomers happen when the naming is different. Okay, their molecular formula would look same, but their name has to be different. Perfect. So that is how you name ketones. Let's see, how would you name this particular structure? So first thing we recognize here is that it has a carbonyl group, which means this is ketone. Second thing I see here is that this is a cyclic structure. So I need to, whenever I see a cyclic structure, it automatically becomes my longest chain or parent chain. So now how would I name my longest chain? This would be cyclo. I see 1, 2, 3, 4, 5, 6 carbons. So it would be cyclohexanone, right? But now where should I start numbering from? This is the only time when your ketone can have number 1. The keto group can be present on carbon number 1s, because remember, we always give preference to the functional group. So in this case, my functional group is 1. Now I could go either from 1, I could go left, or I could go right. Which side should I go? Right, because my other substituent will get the smallest number if I go right. Perfect. So this is 2, 3, 4, 5, 6. So now what is the name of my substituent? It is 1 carbon. So this is methyl. Where is it located? Third carbon. So this is 3 methyl. And what is the name of my chain? Cyclohexanone. So perfect. It would be 3 methyl cyclohexanone. And I don't have to tell where the on is located because it's carbon number 1. Okay. Okay, so let's try to name this particular compound based on IUPAC system. So how would you name this? In this case, first thing we recognize is that this is a ketone group. Second thing I see is I need to find my longest chain. So my longest chain could be 1, 2, and I will be starting numbering from the right side because I want my keto group to have the smallest number possible. This group is also referred to as, not ketro, but keto group. Okay, so this is 1, 2, 3, 4. I could go down, that would give me 5 carbons. I could go straight, that would also give me 5 carbons. So it really doesn't matter. So I'll go straight. Okay, so this is my longest chain. Now, what is my substituent? I have one substituent right here. So what is the name of the parent chain? Parent chain is pentane, but on, pentanone. And my substituent is, I have a methyl group. Where is it located? Carbon 4. So this is 4. So name would be 4-methyl pentanone. On is on 2, so I really don't have to put the 2 here. I could simply name it 4-methyl pentanone, and that would be good. Okay, perfect. Steps are also listed for you, but if you write 2 pentanone, that's also okay, it's acceptable, but most of the times it's not written. Okay. Now let's talk about solubility of aldehydes and ketones. So what do you think? Will aldehydes and ketones be soluble in water? What makes things soluble in water? Water is polar. So anything polar will be soluble in water, anything non-polar will be not soluble in water. So aldehyde and ketones have what group? C double bond O, they have a carbonyl, and we just saw that carbonyl is a polar group. So that means aldehydes and ketones can be polar, and as long as they are polar, they will be soluble. Okay, but what happens whenever you have these groups? The functional groups make them polar, but the R group essentially makes these non-polar. If this R group is too big, the molecule will become non-polar, because even though this part is polar, it reduces its effect is reduced by a long chain of R. Okay, so in this case, aldehydes and ketones are soluble when they have 4 or fewer carbon atoms. So as long as this R group is 4 carbon or less than 4, they will be soluble. But when this R group becomes more than 4, they are no longer soluble, because they have a long hydrocarbon chain which is non-polar, which diminishes the solubility effect of the carbonyl group. So even though the carbonyl is trying to make it polar, but the R group is so long that it cannot win. So in that case, it becomes non-polar. And what makes it? One is that it is polar. Second thing is that it can also make hydrogen bond with water. Why? Because what does aldehyde and ketone have? They have this double bond O. This double bond O is polar, so this is partial negative. And this carbon is partial positive. So we just saw water is like what? Water has, this is partial negative, this is partial positive. So what would happen? The hydrogen from water will make a bond with oxygen of carbonyl group, and this bond will call hydrogen bond, because this hydrogen is bonded to oxygen. As long as hydrogen is bonded to oxygen, nitrogen or fluorine, it can form hydrogen bond with another oxygen, nitrogen or fluorine. So in this case, this will form hydrogen bond. So basically, you can see right here, if this is the molecule of ethanol, ethanol means 2 carbons, so these are black are 2 carbons. This is a hydrogen, this is hydrogen, 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 and this is oxygen. And let me rewrite these as carbon. So in this case, this oxygen has partial negative, and this is water. So this is oxygen, this is hydrogen, hydrogen. They have partial positive charge, water. So hydrogen will form bond with carbonyl. Same is true for ketones. So if this is a ketone, this is carbon, carbon, carbon. This is oxygen. Carbonyl, again, oxygen has partial negative. Water, hydrogen have partial positive charge. So this hydrogen will form a hydrogen bond with keto group. And that makes them to possibly make hydrogen bond with water, which again increases their solubility. As long as they can interact with their solvent, it increases their solubility in that solvent. Yeah. Alright, so that's of aldehydes and ketones. So for instance, methanol, ethanol, propanol, propanone, butanol, butanone, they are all soluble in water as long as they are 4 carbons. But when it becomes more than 4, they become slightly soluble or completely insoluble when it increases. So how you can practice these? Basically see these names and see if you can draw their structures, or draw their structures and see if you can name them. Okay? And whenever you have substituents, just name the alkane and replace the last E with the group that is there. So if it's, in this case it's aldehyde, it becomes al. If it is ketone, it becomes on. Okay. Where do you see these aldehydes and ketones in daily life? Well, one very common example of a ketone is acetone. Acetone, how can you tell this is what kind of ketone this is? Acet means 2 carbons, and on means ketone. But can 2 carbon compound have a ketone? A ketone is C double bond O, and with an H is an aldehyde, right? Ketone was with C double bond O. So a ketone is not possible with 2 carbons. If I put an H here, I make it 2 carbons with the O, double bond O, and I put an H, that becomes an aldehyde. So I have to have a C right here, which means the smallest ketone that is possible is 3 carbons. So even though this is acetone, it is still 3 carbons. It's very confusing. This is the only name where it gets kind of confusing. The rest are very similar. So smallest ketone is going to be an acetone, even though it seems like it's 2 carbon. Ketone with 2 carbons not possible. So this name's a little deceiving, but the rest of the names are usually very easy. This is the time when it gets a little bit deceiving. Okay, so acetone is actually a ketone. Okay, it's used as a thinner. It's used in the nail paint remover. So that's one of the ketones that you use. Where do you see formaldehyde? Formaldehyde would be an aldehyde with 1 carbon. You see it if you have previously seen those bottles where the jars where they store the organisms. Those are usually the liquid in that jar is formaldehyde. It basically fixes everything in your body. So, and inhaling formaldehyde is really bad for us. Just breathing it in is really bad for us. Why? Because you can see wherever it's used as a preservative. It basically just fixes everything in our cell where it is. So if you inhale it, it's basically as you inhale it, it's going to basically freeze whichever cell it comes in, fixes whichever cell it comes in contact with. So that cell's going to die, and it stays as it is. It doesn't change. So it's used as a preservative. Okay. So this is where you probably have seen some of the aldehydes and ketones. Okay, some aldehydes and ketones. These are showing you some examples of aromatic aldehydes. So when you see this particular structure, what you see right here, first thing you see, you recognize this group, which is a benzene ring. It's an aromatic compound, right? So this has, what you're seeing is this particular structure, double bonded structure. So as soon as you see this, you know this is benzene. Okay, and when you see this, you know this is aldehyde group. It is C double bond OH, so it is CHO group. This is aldehyde. So what does the structure become? The structure is basically called a benzaldehyde structure. So this is benzene with an aldehyde. You simply replace this ene with aldehyde. It becomes benzaldehyde. Okay. Then you see this structure, which is basically the essence that you get in vanilla. That is also an aromatic compound. Like I said, aromatic compounds usually are called aromatic because they carry aroma with them. So this is also an aromatic compound, and it's an aldehyde. Cinnamon, the smell of cinnamon is also coming from an aldehyde. It's an aromatic aldehyde again. So you see this group C double bond O. This is actually not an aldehyde. This is a ketone group, right? So here, if nothing is written, that means it's a carbon. It's not a hydrogen. So that means this is a carbon, this is a carbon. So this is C double bond O, C double bond O, C, which means this is ketone. Okay. So benzaldehyde, where is benzaldehyde found? It's found in almonds. So you know almonds have that aroma to them. Sometimes if they are like rotten, very bad aroma. So that is also coming from aldehyde. Okay. This fragrance in vanilla and cinnamon is also from aldehyde and ketones. Okay. All right. So moving on, even though this name says aldehyde, I might have to check this, because if this is the structure, then it's a ketone. Of course, I don't expect you to memorize this, but yes, benzaldehyde, you should be able to draw the structure, but I don't expect you to memorize any of this. But I would have to check, because the name says aldehyde. If the name says aldehyde, it should have been an H here. It might be like a typo or something in the book, but if it was an H, it would be aldehyde. If it is a C, then it should be a ketone. Okay. All right, so let's quickly try some questions. Classify each as an aldehyde or a ketone. So what would this A be? Aldehyde or a ketone? Ketone, perfect. It is C double bond O without any hydrogen. It has carbon on both the sides. How about this? Aldehyde, perfect. How about this? Aldehyde. Good. and this would be ketone, because there is carbon on both the sides of this ketocarbon. Okay, let's try to name them. How would you name this?
It would be
How many carbons is it in total?
It's 4 actually.
4. Yes. So, and where do we start numbering? From this side, because this would give my substitute, not a substituent, but a functional group, the smallest number. So 1, 2, 3, 4. 4 carbon means butanone, and it's on second carbon, so I really don't have to put the number. But if you do, it's okay. 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 How about this? If we name this 2 carbon. So 2 carbon prefixes. Yeah. No. Yeah, that's where usually students get confused. Like they know the prefix, but they don't know how to follow it up. So usually name the alkane and replace the E with O. So ethane, and then E becomes O. So ethanol. Okay. So how about this? C. So here what we'll have to do is, we can see this is aldehyde first thing. Now I need to find my longest chain and name my alkane. So my longest chain would be that. You could eyeball it right now, but we should also confirm it by checking the numbers, right? So I would say 1, 2, 3, 4. 4 carbon. If I went from 1, 2, 3 up, that would also give me 4. If I went 1, 2, 3, 4 down, that's also giving me 4. So maximum is 4, which means my parent chain is butane, but with O. So it's butanol. Now I name my substituent. I have 2 substituent. Where is this? And it is? Yes, perfect. So this is 3. This is also 3 methyl. So it becomes dimethyl, and it would be 3,3 dash dimethyl butanol. Okay. How about this ketone? How do we name this? Perfect. This is 6 carbons. 1, 2, 3, 4, 5, 6. So this is, and it's a cyclic structure. So if I was naming the alkane, it would be cyclohexane, right? But this is on. So instead of E, I would write hexanone. And it's located on carbon number 1. So you could write 1 cyclohexanone, or you could simply write cyclohexanone, and that also tells me this is on carbon number 1. Okay, so that is how you would name and ketone. Let's name these. These should be fairly simple. So A would be, first thing, what is this functional group? Ketone. Perfect. So it has to end with on. Now let's find our longest chain, which is, should I number from the left or from the right? From the right. So my substituent gets the smallest number. So it is 1, 2, 3, 4, 5, 6, and the name would be hexanone. And you could write it as 2-hexanone, or you could simply write hexanone. That would do. Okay, let's name the next one. Again, this is a ketone, and my longest chain now is 1, 2, 3, 4. This is a chlorine. Sometimes people confuse that this is carbon with an I. It isn't, because it should have hydrogens as well, right? So this is chlorine. So my longest chain is this, which means what is the name of the parent chain? Perfect, butanone. I don't have to tell that's on second carbon, but I do have to tell my substituent, which is perfect. So this is 4-chlorobutanol. Okay. Next, we'll talk about some reactions that aldehydes and ketones undergo. And one of those reactions is oxidation of aldehydes and ketones. And because of this reaction, they do give us positive result for some test. There are a couple tests that we'll talk about. The first test here, which can help us in identifying an aldehyde, is called a Tollens test. So a Tollens test involves a reagent which is called Tollens reagent. This basically consists of silver ion. Silver ion is Ag+. So whenever any aldehyde reacts with silver ions, it is oxidized to produce an acid. So if you remember, the definition of oxidation was, in organic chemistry, the definition of oxidation is we increase the number of bonds between carbon and oxygen. Either you increase the bonds or addition of oxygen or removal of hydrogen. All these are definitions of different definitions of oxidation in organic chemistry. So in this case, what is happening? We have an aldehyde, for instance, you can see right here. You don't care which aldehyde it is, as long as it consists of this aldehyde group, which is CHO group, it will be oxidized, and usually that is written like an O in square parentheses. So this will oxidize and it will form RCOOH. So this O is added right here between carbon and hydrogen. Of course, chemically this is not what is happening, but whatever the mechanism that is happening here is out of your course. So for you guys, what you can remember is whenever an aldehyde oxidizes, it would produce carboxylic acid. So this is where I'm introducing another functional group to you guys, which is called RC double bond OH. So this is where a carbonyl group is attached to an OH or a hydroxyl group. This group is called as a carboxylic acid in organic chemistry. Okay, so this is a new functional group. We'll talk more details about this functional group later on. But for now, what you need to remember is whenever an aldehyde is oxidized, it converts into carboxylic acid. Okay, so who does this? Tollens reagent. Tollens reagent is an oxidizing agent. So this is oxidizing aldehyde, therefore it is called an agent which is oxidizing aldehyde. It's called oxidizing agent. So remember, this is an agent. For instance, when you go to buy a house, who is buying the house? You are buying the house. So who is the purchaser of the house? You are purchasing the house and you are the purchaser. And who is the agent who is giving you the house? He is the real estate agent, right? So he is the person who is helping you purchase the house. So that's what's happening here. Aldehyde is getting oxidized, and who is helping oxidize aldehyde? Tollens reagent. So this is the agent which is oxidizing or helping aldehyde in oxidizing, therefore it is called an oxidizing agent. So what happens to the agent? The agent itself gets reduced. Okay, so whenever remember in redox reaction, one molecule has to oxidize, the other has to be reduced. So in this case, aldehyde is getting reduced and the other reactant here is Tollens reagent, which is getting reduced. So whenever you see silver ion present, it will be in reaction with an aldehyde, it will get oxidized to produce carboxylic acid. So simply convert this CHO group into COOH group, and whatever is attached to this carbon stays as it is, nothing changes there. So for instance, here this was CH3 attached to aldehyde group, here also it is CH3 attached to carboxylic acid group. Okay, and what happens to silver? Silver here was Ag+, silver has been here reduced to silver metal. So silver metal is solid, silver ion is of course going to be aqueous solution. So what happens here, if you add aldehyde into the silver ion, it will reduce silver to convert it into silver metal, and therefore a shiny metal will start depositing in the container. So this tells you that an aldehyde is present in the solution. So this is a very commonly used test to identify or detect presence of aldehydes. But these aldehydes, this reagent can only oxidize aldehydes. It cannot oxidize ketones. This is very crucial. Ketones cannot be oxidized. In order to oxidize something, you need to. Why can't we do this with ketone? Because a ketone would consist of carbon. Let's say I take the smallest ketone, C double bond O, CH3. So in order to oxidize, this carbon has the oxygen, but it needs to have one hydrogen attached to it. Since it does not have a hydrogen, we cannot further oxidize this particular compound. Therefore, ketones cannot be oxidized, but aldehydes can be oxidized to carboxylic acid. Okay. The next test is called Benedict test. This is also a test to identify presence of aldehyde, but this test is specific towards one specific type of aldehyde. It will only give a positive test with the aldehydes that have an adjacent hydroxyl group. Okay, so what that means, the carbon which has the aldehyde group, there has to be a adjacent carbon which has a hydroxyl group attached to it. So for instance, if we see right here, when you look at this molecule, this has, first thing we recognize, this has an aldehyde group and it's an alkane, but with an aldehyde. So this is an aldehyde. And what does this have? It has a adjacent carbon, which is the carbon next to the aldehyde carbon, has the hydroxyl group. So a aldehyde which has the hydroxy group next to the aldehyde group would be the one which will give a positive test with Benedict reagent. Any other aldehyde will not give a positive test. Only aldehydes which have the adjacent hydroxyl group will give positive test with Benedict reagent. And what is Benedict reagent? Benedict reagent consists of copper ions. So in case of the Tollens test, we saw it consisted of silver ions, and here it consists of copper ions. Here again, what is happening? The copper ions will oxidize our aldehyde, and aldehyde will be converted into, again, an acid. So what is happening here? Everything else stays the same. So CH3CHOH, CH3CHOH, this stays the same. Only thing that happens here is carbon double bonded O, we add one more oxygen right here, so it becomes C double bond OH. So again, aldehyde will be converted into acid. And what would happen to copper solution? This copper 2 plus solution will be reduced. This is reduced. This is reduced to produce Cu2O, which is copper oxide. Okay, so aldehyde is oxidized and Benedict reagent is reduced. And what happens here in this case, the interesting thing, you can actually see it by eyes if the aldehyde is present, because the reagent changes color. So this copper 2 plus ion is blue in color, whereas copper oxide is brick red in color, like you see right here. This is brick red, so color would change from blue to red, and this becomes a solid. So if there is an aldehyde with an adjacent hydroxy present, it would give a positive test for Benedict reagent, whereas the test is negative with simple aldehyde and ketones. It would not give a positive test for ketone either, because we know ketones cannot be oxidized. All right. So for instance, you can see right here, Benedict test, the blue color, Cu2 plus is blue, it changes to brick red color, which is copper oxide. So this test is usually used to test for presence of sugars. Why? Because this is, for instance, this is the structure of a glucose molecule. So you can see right here, it's an organic molecule. It has C, 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 C. It has 1, 2, 3, 4, 5, 6 carbon atoms, and each of those carbon atoms have hydrogen or a hydroxy group or a hydrogen group. And then you see the functional group right here, which is aldehyde CHO. So this sugar is basically an aldehyde. And what else do you see? The adjacent carbon here, which is this, has a hydroxy group attached to it. So this will give a positive test for Benedict reagent. So basically sugars like this usually give Benedict test for a positive test for Benedict reagent, and that is why these sugars, this test can be used to recognize the presence of or detect the presence of sugars in solution. Okay, so the questions could simply be asked as an aldehyde or a ketone would be given to you, and the question would be, would this give a positive result for Benedict test or a positive result for Tollens test? So what you need to remember is that Tollens test is given by a positive Tollens test, I would write positive right here, is given by any aldehyde, whereas Benedict test is given, it only gives positive if the aldehyde has hydroxy on the adjacent carbon. And ketones basically are negative for both tests. Okay, so this can be used to differentiate between aldehydes and ketones, these tests. Okay, so this was oxidation of aldehyde and ketone. Next we'll talk about reduction of aldehyde and ketone. In reduction of organic compounds, what is reduction? The opposite of oxidation. The number of carbon-oxygen bond is reduced by addition of hydrogen or loss of oxygen. Reduction can happen two ways. Either it would add a hydrogen or it would lose an oxygen. Okay, and how do we reduce? Reduction is usually done in presence of a catalyst. Again, catalyst would be like a metal, nickel, platinum, palladium, and addition of hydrogen. Okay, so the reagents that are usually used for reduction are reagents like sodium borohydride, which is NaBH4, or you would simply see hydrogen written as one of the reactants in presence of these catalysts. And how these reduce? So right here you can see this. When you look at this molecule, what is this? This is an aldehyde. It consists of CHO group with two other carbons. Okay, so when hydrogen is added, what would happen? This is an example of a reduction. You see a catalyst which is platinum. You also see hydrogen being added. How would hydrogen add? Hydrogen has two hydrogen atoms. So one of these hydrogen atoms will go and attach to this carbon. One of these double bonds would break. So now carbon, if I break this double bond, this oxygen has one more extra bond and this carbon will have one more extra bond. Why? Because oxygen always makes two bonds. If I break one of these bonds, oxygen now only has one bond. So it will have one empty bond which it wants to make with something. Same thing happens to carbon. What would happen? This hydrogen, one of the atoms will attach to this oxygen. One of the atoms, the other atom would attach to carbon. So what would your molecule look like now? CH3, CH2, C, single bond OH, and this would be H and this would be H. So I can rewrite this as CH2, right? So what is this molecule now? This is an example of alcohol. This is the long chain and this is hydroxyl group. So this becomes an alcohol. What does this tell you? This tells you that an aldehyde always reduces. I would write reduction like this, or you could write it in hydrogen. It reduces to form alcohol. Okay, and the interesting thing here is, remember how aldehyde is always the terminal group, which means the alcohol will always be the terminal group. So this will always form a primary alcohol where the carbon only has one more carbon or alkyl group attached to it. Remember, primary alcohols are the alcohols where the carbon which has hydroxyl group is attached to one more alkyl group. Okay, one more carbon. So this will always form a primary alcohol. What happens to ketones? For instance, you see right here, this is a ketone, CH3C double bond of CH3. So if I add hydrogen to this, how would I add hydrogen? This one double bond would break. One hydrogen will go to H, one hydrogen will go to C. So the compound that will be formed would be CH3C. This hydrogen would become CH. This O will become OH, CH3. So what kind of alcohol is this? This is a secondary alcohol. So you can see right here, this is this carbon is attached to 2 more carbon or 2 more alkyl groups, therefore this is a secondary alcohol. So whenever ketones are reduced, you could put hydrogen or you could write as R. This would always form a secondary alcohol. So remember this. Ketones after reduction form secondary alcohol. Aldehydes after reduction form primary alcohols. How could I ask you a question? I would just simply give you this reactant. I could replace this aldehyde with any other aldehyde, and I will ask you what would be the products produced by reduction of the aldehyde or in presence of hydrogen, in presence of platinum, nickel, or palladium. So you should know that aldehyde would always be reduced to give primary alcohol, and ketone will be reduced to give secondary alcohol. How do you memorize it? Whenever you see hydrogen written like this, it means you have to add hydrogen into the compound. Where can you add hydrogen? Wherever you see double bond. You simply break that double bond and you add hydrogen to the 2 atoms that were involved in the double bond. Okay. So for instance, let's see a question like this. Select the product for oxidation of the following. So what do we see here? This is a reaction of oxidation. The question is asking what would be the product. So what we see here is 1, 2, 3, 4 carbons and a hydroxy. So this is alcohol. How do alcohols oxidize? Alcohols will oxidize by simply, we have seen this reaction in the previous chapter, alcohols will oxidize by removing the hydrogens. So this hydrogen and the adjacent hydrogen will be, adjacent carbon hydrogen will be lost, and oxidation means removal of hydrogen. You have to remember these definitions. Either you have an opportunity to remove hydrogen or you had an opportunity to add oxygen, oxidation, so add oxygen, or you increase the number of bond with oxygen. So in this case what we'll do, we will get rid of this hydrogen, so hydrogen will be lost, which means this carbon will now have 1 extra bond, this oxygen will now have 1 extra bond. So what are they going to do? They will form this extra bond with each other, so they'll form a double bond right here. So what is happening here? Hydrogen is removed and a double bond is formed between carbon and oxygen. So the number of bond between carbon and oxygen is increasing. Okay, so again what is happening? This hydrogen will be lost, this hydrogen will be lost, and will lose hydrogen. Okay, H2. Now this oxygen has 1 extra bond, this oxygen needs 1 extra bond, this carbon needs 1 extra bond, so they will bond with each other and the molecule, rest everything stays the same. The molecule will become C double bond O, CH2, CH3. So what is this? This is alcohol. What type? Secondary alcohol. On oxidation will produce ketone. So we saw this reaction in reverse right now. We saw that when a ketone is reduced, it becomes secondary alcohol. So these 2 reactions are basically opposite of each other. Remember, reduction, one is reduction and one is oxidation. They are always opposite of each other. So if an alcohol is oxidized, it will form ketone. Which type? Secondary alcohol is oxidized, it will form ketone, and if the ketone is reduced, it will form secondary alcohol. So it goes both the ways. Okay, so it is just the opposite of what we saw. So your answer here is going to be B. Okay, moving on. Okay, the answer to that. So for instance, let's try this question. Select the product when this particular alcohol undergoes each of the following reactions. So what is happening here? We have this particular alcohol, CH3, CH2, CH2OH. This is undergoing oxidation to produce B, then it further undergoes oxidation to produce C. So if you remember alcohols, you can make this chart if you want. Alcohols oxidize to form aldehyde, and then they turn into carboxylic acids. Okay, this is when you have primary alcohols. If it is secondary alcohols, they oxidize to form ketones, and ketones cannot be further oxidized. Okay, remember this, we cannot oxidize them. Why? Because they don't have that hydrogen to get rid of. Whereas reverse is also true. So ketones can be reduced to form alcohols, and carboxylic acid can be reduced to form aldehyde. Aldehyde can be reduced to form primary alcohol. So it goes both the ways. If you remember this chart, you could solve all these questions. So what do we have here? I have an alcohol. It's a primary alcohol. Under oxidation, I know it produces aldehyde. So what would happen? This right here will turn into aldehyde. How? This hydrogen will be lost and it will form a bond right here. This oxygen will be double bonded. So let's rewrite that molecule. So the first molecule would be CH3, CH2, CH2, double bond H. So essentially this would be our molecule. Oh, this hydrogen and this hydrogen will be lost, so it will become C double bond H, CHO. So this is, where do we see this? This is option number 3 right here. So B is 3. Let's look at what would be a final product. Aldehyde convert into carboxylic acid. So everything else stays the same. You just simply change this group into carboxylic acid. So CH3, CH2, C double bond O, it will turn into OH. So that would be our group C. Do we have that? That is 4. So answer for this would be 4. Okay. So always remember, if you can't remember what is being lost, how it is being lost, just remember that it would be, you have to convert alcohol into aldehyde and simply write the aldehyde that is formed from there. Okay. All right. Okay. For instance, a question could look like this. Give the primary product for reaction of 2-propanol when it undergoes oxidation. So 2-propanol is undergoing oxidation and dehydration. So actually you weren't here for the part of alcohol reaction. We did cover these in alcohol, and I think this is a part of alcohols because it's a single chapter, so it's kind of like repeating here, but we'll work through these. So 2-propanol, first let's draw the structure for 2-propanol. Again, we are going structure, so I'll start from the end. All means alcohol, so it has to have an OH group. Prop means 3. Perfect. So I draw 3 carbons. And where is the all located? Second carbon. So I'll draw OH right here. Rest I'll fill it up with hydrogens. So this carbon has 1 bond, so it needs 3 more. This carbon has 3 bonds, it needs 1 more. This carbon has 1 bond, so it needs 3 more. So that is the structure of 2-propanol. Now the question is, what is the oxidation product? So oxidation, again, either we remove hydrogen or we add oxygen. What can we do here? Remove the hydrogens. So we remove this, and our product would be CH3, C double bond O, CH3. So we will have propanone, a ketone, right? Oxidation of alcohol will produce, secondary alcohol will produce ketone. Then we have dehydration. Dehydration means removal of water. Hydration means water. When you're hydrating a reaction, you're adding water. When you're dehydrating it, you're removing water. So we have to remove water from this compound now. CHOH, this was our alcohol. We have to do dehydration. How would we remove water? When you remove water, hydroxy group comes from this carbon and a hydrogen will come from an adjacent carbon. Okay, and which adjacent carbon? The rule is actually poor gets poorer. rich gets richer, poor gets poorer. Okay, so the carbon that has less hydrogen will get even more poor, so it will lose the hydrogen. Okay, that's the rule. The carbon that has less hydrogen. In this case, luckily both the carbons have same number of hydrogen, so you could choose any one. Okay, so let's say I choose this carbon. One of the hydrogens will be lost. What will be left? CH2. This will be CH3. So now this hydrogen is lost, so it has one extra hand. This hydroxy is lost, so this has one extra hand. And what was lost is water, because hydroxy from here, hydrogen from here, HOH is H2O. So water is lost. And what would happen? This extra bonds that they have, they are going to make bond with each other. So it will turn into alkene. Whenever alcohols are dehydrated, they turn into alkenes. Okay, and the rule is poor gets poorer. So for instance, in this question it's easy. What if I change the question and I made it CH3 CH2 CH3 OH? In this case, if I ask what is the dehydration product, hydroxy is lost from here and hydrogen will be lost from either one of these. Now this carbon has 2 hydrogen, this carbon has 3 hydrogen. The rule is poor gets poorer. So this already is poor, it has less hydrogen, this will lose the hydrogen. So the double bond that would be formed will be between this carbon and the hydroxy carbon. Okay, so that was alcohols. Okay, right. Okay, so for instance, this is the question. Write the structure and name of the organic product when each is mixed with Tollens reagent. So when these compounds are mixed with Tollens reagent, what is the product, what is its structure, and what is its name? So Tollens reagent, remember, is what? It's an oxidizing agent. So it is going to oxidize our compounds. So butanol means aldehyde. So let's draw the structure of butanol. Perfect. 4 carbons. One of those has to be the aldehyde, and rest we fill up with hydrogen. So 2 hydrogen here, 2 hydrogen here, 3 hydrogen here. So that is butanol. Oxidizing basically means this will be converted to this. So what is the product? This is the product. What is the name? Name, basically whenever you're naming the organic acids, their name, you replace essentially the end with oic acid. Okay, so in this case, same thing. You would replace the E, alkane. You replace the E with oic acid. So in this case, if this was an alkane, it is 1, 2, 3, 4 carbons. So butane, but it would become butanoic acid. Okay. Then the next one is we are oxidizing acetaldehyde. Acetaldehyde, acet was 2 carbons. Perfect. Aldehyde means there is an aldehyde group. So 2 carbon aldehyde, one of these has to be the aldehyde group, and the second one would be CH3. So it's a 2 carbon aldehyde. And we are oxidizing it. So what would be the product? This hydrogen will turn into OH. What would be the name? 2 carbon. So we know 2 carbon is ethane. In this case, it's ethanoic acid. Perfect. Then we have ethyl methyl ketone. Okay. I know we only learned the IUPAC names for ketone, but this is the common name. Of course, I will never give you this, but let's try this question. It's fairly simple when you talk about ethyl methyl ketone. Ketone has ethyl group and a methyl group. But what do ketones undergo? Do ketones undergo oxidation? No. They only undergo reduction. So Tollens test, no reaction. Ketones are not oxidized by Tollens reagent. Simple. Okay. Perfect. Next we'll talk about some more reactions between which is called addition of alcohol. Okay. This is the reaction between alcohol and an aldehyde or a ketone group. Okay, so these reactions basically produce hemiacetals or acetals. These are very, very common when we talk about sugars. They exist very commonly in sugars. So what is a hemiacetal group? A hemiacetal group is formed when one carbon consists of two functional groups. It contains an OH group and an OR group on the same carbon. Okay, so it has to have an OH group and an OR group on the same carbon. That is called a hemiacetals. How are these hemiacetals produced? We'll look at the reaction as well. When an alcohol reacts with an aldehyde or a ketone in presence of acid catalyst, it would produce hemiacetal. So whenever alcohol reacts with aldehyde or ketone, it is going to produce hemiacetal. It consists of both OH and OR group on the same carbon. Okay, but these hemiacetals are very unstable. You can't separate those. Usually they would react with another molecule of alcohol to produce acetal. Okay, so hemiacetals are generally unstable. They would react with the second molecule of alcohol to form a stable acetal group and water. And what do acetals consist of? Acetal basically consists of two OR groups on the same carbon. Okay, so let's look at the reaction. For instance, like this, if this is aldehyde and we have one alcohol, so this aldehyde group right here and this alcohol group will react with each other to produce a hemiacetal, which consists of OR group and the OH group on the same carbon. So what is happening in this reaction essentially? In this reaction, this bond is breaking. Okay, when we break this bond, this hydrogen from this reactant is going to go and react with this oxygen and convert it into alcohol, and rest, whatever is left, you would add that to this particular carbon. So this whatever is left would become OCH3, and this hydrogen will go to oxygen, and this bond would be broken, and your product would basically consist of carbon with hydroxy and OCH3. Okay, again, mechanism, you could look for mechanism, but that's going to be very extensive for this course, so we're going to not focus on mechanism. Essentially what is being produced here? A hemiacetal. Whenever an alcohol and an aldehyde react, it produces hemiacetal, but hemiacetal is not very stable, so it would react with another molecule of alcohol. And how would it react in this case? Water will be lost. This H and this OH will react with each other to produce water, and we will be left with CH3, or you could say this OH and this hydrogen. This hydrogen and this OH will react with each other to produce water, HOH, and whatever else is left again is going to react with this particular carbon. Okay, so you would have one carbon with two OR groups, and this is called acetal. Okay, again, it's a lot of arrow pushing. It's not one single step reaction, but we'll not focus on that. Okay, where I will not be asking you much of the question for this in this form, but I will probably majorly ask you questions when it comes to carbohydrates. You'll see it is very prevalent there, but you should at least know what is a hemiacetal, what is an acetal, when is it produced, theoretically. Okay, so let's look at another here. For instance, like this. This is very commonly happens in case of sugars. So a reaction, sometimes this can happen within itself, like a molecule. If you can see, look at this molecule, it consists of an aldehyde group right here, and it also has an alcohol group. So within one molecule, when you have an aldehyde group and an alcohol group, it can react with each other. You don't need a second reactant. The molecule will react with itself. So what would happen in this case? This aldehyde would react with this OH group, and it would form a cyclic hemiacetal. Okay, so what is happening? You can see right here this, what was happening in when an aldehyde and alcohol was reacting. Essentially this hydrogen was given away, right, to this hydroxy. This hydrogen will go here, this bond will break, and this O is going to react with this carbon. Does this make sense? Let me repeat that. So if you remember, in case of a reaction of aldehyde with alcohol, this bond was breaking between carbon oxygen. So now oxygen has one extra bond, carbon has one extra bond to make. So this hydrogen that is here is going to go to this carbon, and this molecule, this oxygen, is now going to react with the carbon. So essentially the molecule is bending together. So you can see right here, this molecule is bending around each other, and it will form a compound which is a cyclic hemiacetal. And this is formed when one compound has both aldehyde and the alcohol group on itself. Okay, so these cyclic hemiacetals are pretty stable and they can be separated. So they don't undergo another reaction to form acetal. They are very stable. And seen in case of carbohydrates, which is sugars. For instance, glucose, fructose. All those sugars can form hemiacetals. They will form a 6-membered or a 5-membered ring to form hemiacetals. Okay, and we'll talk about this further in that chapter. So I'm going to kind of here. So for instance, you can see this is again the molecule of glucose. It has this alcohol group on this carbon, carbon number 5, and this is carbon number 1, which has the aldehyde group. So this aldehyde would react with this particular hydroxy. So this hydrogen will be lost, this bond will be broken, hydrogen will come here, and this oxygen is going to form a bond with this carbon. So the molecule is going to rotate by within itself, and it will form a hemiacetal. So glucose, the glucose that is present in our body that we consume, 99% of that glucose is in the form of this cyclic structure, cyclic hemiacetal. Only 1% of it exists like this open chain. This is called an open chain structure. 99% of this exists as hemiacetal. Why? Because these are more stable. Okay, so that is where hemiacetals you would usually find them. Okay, then we have another reaction you could have. An alcohol can further be added to this hemiacetal, and it can form a cyclic acetal as well. Okay, usually it is not, because these are cyclic structure, they are not as unstable as the previous hemiacetals that we saw. Those cannot be isolated, they directly react with another alcohol, whereas these cyclic hemiacetals can still be isolated, but they can further react with alcohol. It's the same reaction. Now water will be lost. Essentially this hydrogen and this hydroxy will be lost to form water, and whatever rest is there is going to react with the carbon. So compound like this would be formed, which is called a cyclic acetal. Okay, this reaction again is found a lot in sugars, where you would see that some sugars will join with each other to form polymeric sugars. Okay, we'll again talk about those in carbohydrates. Okay, so for instance, one glucose and one glucose will form a bond with each other. So this was a cyclic acetal. Second cyclic acetal will join with each other to form a acetal, which is a sugar called maltose. So sugars and sugars can react with each other to form another kind of sugar. Okay, so again, this is something which we'll again talk in detail in carbohydrates. You don't have to focus on these reactions. Only thing you should know is what is an acetal, what is a hemiacetal, how are they produced. Okay, not these. Don't focus on these sugars. We'll worry about sugars in carbohydrates. Okay. Okay, so here identify each as a hemiacetal or an acetal. So which one would be the hemiacetal? One that has, it has to have, carbon has to have an OH group and OR group, right? And what is an acetal? An acetal is where the carbon has OR and OR. So it consists of two OR groups. So out of this, is it a hemiacetal or an acetal?
That would be a
Hemiacetal, perfect. It consists of an OH and OR. R essentially means any carbon chain. Okay, how about this?
the acetal.
Perfect. This is an acetal group. It consists of two OR groups on the same carbon. So this is acetal. Is the acetal produced? Reaction could look like this. Draw the condensed structure formula for acetal, which is formed by adding CH3OH to butanol. Okay, so butanol is the aldehyde, CH3OH is the alcohol. They will react with each other to produce hemiacetal and then the acetal, right? The question is asking what would be the product produced. So essentially the first reaction, if we do this in steps, let's write what would butanol look like. It would be 4 carbons with one of those carbons being the aldehyde and rest would be hydrogens added with hydrogens. Then we have a CH3OH group here. How would this react? This hydrogen, again remember this bond is going to break between carbon and oxygen. So I would break this bond, CH3, CH2, CH2. It would turn into one single bond between oxygen and there was this hydrogen right here, right? So this hydrogen will go and interact with this particular oxygen. Let me rewrite, if I write this in a different color, CH3OH. So one hydrogen will go here and what is left from here is this CH3O. So this CH3O will go and bind to carbon. So that would be our hemiacetal. Now this is going to further react. It's not stable. The question. So now what would happen? This is unstable. So it will further react with another CH3OH, right? So let me write that in another color now. CH3OH. In this case, water will be lost. How? This hydrogen and this OH are going to form water and we will have H O H, which is essentially water. This will be lost and rest everything else will join with each other. So we'll have everything else stays the same, CH3, CH2, CH2, C and this hydrogen, and it had this OCH3 from before, and now we will add this OCH3 which is gone is added here. So we will have OCH3. Okay, so that is how this reaction would occur. So now your product is acetal. It has two OR groups attached to the same carbon. Okay. Any questions?
No, I think for now,
Okay. Think that